Okay, thank you very much, Jorge. And I really admire Jorge for his beautiful action, scientific or patriotic. And I hope to make my small contribution to receive students from Peru and to develop collaboration. So as Jorge mentioned, I am from the same lab, GEMaC. And you know, we are located in Versailles. Here's a photo of our lab. You know, Versailles Palace and architecture is quite different, unfortunately, of our lab, but still we are doing quite interesting and useful things, I hope. So my talk will be very general to show you what is the challenge for oxides in science of conductivity, which is main parameter for electronics, let's say. And when San made a very nice introduction about semiconductors conventional, which we know from last century played a very crucial role, like silicon, indium, independent, and so on. So I will speak about wide band gap oxides and generally wide band gap materials, which, as Vincent mentioned, there are materials which have band gap more than 3 electron volts. So they can have absorption in UV and deep UV regions. So there are many of them. Oh, sorry. Which we call wide band gap materials, as Vincent already mentioned, zinc oxide, zinc selenide, zinc sulfide, and so all this family of materials. And there is also now very important new family of materials, what we call ultra wide band gap. It means wide band gap materials which have even higher band gap, more than 4 electron volts. And it's a diamond, well-known diamond, gallium oxide, boron nitride, aluminum nitride, which are very fashion, let's say, and under research today. So they are important wide band gap materials because they can have higher operation temperatures than silicon and conventional semiconductors. The devices based on this material can have higher radiation hardness, high operation frequency, high voltage operation, and it was very interesting. In 2014, even President of USA had a very nice talk about wide band gap materials, and yeah, it was really well written, and he was speaking how important it is for industry wide band gap materials. And in fact, 2014, huge funds were released in the United States to fund technology development of wide band gap materials, especially for power electronics. So what is in fact the application of wide band gap materials? It's very, very broad. So it's data sets, renewable energy, electrical cars, electrical trains, and so on. So it's huge, really huge market, which is targeted by devices based on wide band gap materials. And it's important also to underline, where is it? Also, underline that since nowadays it's very important also to decrease CO2 emission. It was well shown that devices based on wide band gap materials should have much lower CO2 emission. So let's say they are considered kind of materials which can give us green technology. So now I will focus on oxides, which are wide band gap oxides, and still we have a huge application area, as you see, and I will divide by two, which is more close to my field of research, is photovoltaics and power electronics. So in photovoltaics, OA can be used, as my son also mentioned previously, for example, zinc oxide and generally oxide can be used in transparent conductors as barrier layers, and they can have some unique properties which will be very important for photovoltaic application. And for power electronics, the same. It's new trend to use wide band gap materials, and especially oxide, and I will show you why gallium oxide is really future of power electronics. Okay, so as you know, in every electronic material we have N-type and P-type, so to have a device which can operate and show fully potentiality is important to have p-n junction. So p-n junction is kind of building block of every electronic device. So what does it mean in material science? That it means we should have material which can exhibit N-type and at the same time exhibit P-type conductivity, of course, by changing doping. Usually we dope differently to have N and P-type material. So for oxides, big problem is that there is asymmetric tendency of doping. What does it mean? That oxides, they tend to be doped very easily to be N-type, but there is problem of P-type doping in oxides, and I think he skipped slides showing that zinc oxide is really more than century maybe already challenged to be P-type, but still is a problem. But it's a really general problem of oxides because the nature of oxides tends to be this way, because in the chemical formula we have oxygen, and this oxygen which has 2p electrons that makes problematic of doping. But still many effort has been done to get P-type oxides, and here I listed some of them which already demonstrated. P-type is Delafoside, family of Delafosides, and strontium kappa oxide, for example, aluminium kappa oxide. There are family of Delafoside oxides which has P-type conductivity, but problem is mobility is very, very low. Kappa oxide, which is classical P-type oxide, SNO, spinel, family of spinel structure oxides has been discovered as P-type, and a very famous nickel oxide. So here is all application what can be targeted by oxides, and you see it's very, very broad. Many oxides what I listed, they were demonstrated P-type and the devices also, but many still are, let's say, in lab level, so TRL3, not more. So I would like to make more clear, so I divided in two parts what is really challenge of oxides for conductivity. One I can call technological challenge to fabricate P-type materials. So as I said, difficulty is that high formation energy of native acceptors. So it means to create acceptor we need a lot of energy, and material makes obstacle to this action, so it's very difficult to create acceptors. and the same time is very low formation energy of donor. So it means if we want to force material to be p-type, material has tendency to make an obstacle to create electrons to cancel the effect of p-type doping. So unfortunately there is general trend for oxides, though there is a very beautiful exception, and I will show you this. And second is very curious, but fact is that maybe even we produce p-type materials, the problem is to put in evidence that it's p-type. So it means you will have to have possibility to measure positive hole voltage, and that is very often very difficult. And my dear student is here, and she can confirm that we have really always need to fight to show that, to put the evidence that material is p-type. Why, in fact, by measurement technique, what makes difficult is that materials usually which are p-type, they are highly resistive, and their carrier mobility is very low. So it means when we are doing Hall effect, which is primus inter pares to show Hall conductivity, but general type of conductivity, it's very difficult to extract Hall voltage from these materials. So that was the reason that in GEMaC, which is we are specialists during many years in wide bandgap materials, that was the reason of development of special instrumentation which are dedicated to measure high resistive materials and also materials with low mobility. So first is Seebeck effect, is thermal power, which is very fast, non-invasive method, so very quickly without any electrical contact we can say material is P or N type. But we can't say how much carriers, mobility and so on, but it's very useful what we use to have first hint if fabricated material is P or N type. Second, and it was developed homemade, it's specially developed for high impedance materials. The second is Hall effect and resistivity in van der Pol configuration, and we can measure up to 10 giga ohm resistance in 1.6 Tesla field with from 80 to 850 Kelvin temperature range and different atmospheres, because very often we are putting during the measurement, we want to know how material reacts at different atmospheres, so we have this possibility. And software also specially was created in GEMaC to pilot this equipment. And the third one is it's conventional PPMS physical property measurement system from quantum design, but which was updated specially for high band gap materials. It means for very resistive materials. And you can see when we bought, we could measure up to mega ohm resistance. After option which I call tornado, we can measure up to 10 giga ohm. So difference between tornado and previous, what I show is here we can apply 9 Tesla magnetic field, and the current we can apply is picoampere, while in previous one is nanoampere. And also the same equipment was developed a photo-optical probe, so we can illuminate material and with any light, of course, and measure photoconductivity and even photoluminescence. So we did also application, special application, which you can see in quantum design website. So here is all countries which I have pleasure to collaborate, and I hope that Peru will be added very soon to this list. And if you find useful, we are very open for collaboration on wide bandgap materials, especially oxides. Here are some examples which kind of problems we are looking for. For example, very often we are working with magnetic oxides, so it's combination of very nice combination of electronic properties with magnetic properties, and one of the examples is collaboration with Strasbourg, when we could show that ferromagnetic material can be N and P type depending on growth conditions. So it was measured this N and P types thanks to our instrumentation. And the second example, transparent conducting oxide, which are P-type. Also here difficulty is not so resistivity but very low mobility, which needs to have special instrumentation and special methodology to apply. And so we have this possibility to, as you see, to measure very low mobility, below 1, to extract correctly the value of mobility. So that was just briefly to say you which kind of materials we are working. So now, as I mentioned, oxides have huge application and potentially can be applied in many different fields, but as you know, between invention, what we call in the lab, and innovation, it means to go to the market. It's a very huge gap, and that gap is related, that is permanent battle between device performance and its cost. And for example, for power electronic devices, it was estimated that cost of power device includes 78% of material fabrication. So it means that material, one thing is to have very performant material, but second, we should keep always in mind that important is cost of fabrication and cost of raw material. And for example, speaking about power electronics, if we take power electronic device, DC-DC or AC-DC current converter, which is monopolar, it means which works only N-type, for example, like MOSFET or diode. There is very famous Baliga figure of merit, which here you can figure of merit is specific on resistance and breakdown voltage, two very important parameters for power device. And here is a landscape of materials, so as a reference, where you hold silicon and wide band gap like silicon carbide, gallium nitride, diamond, gallium oxide, and boron nitride. So what's our interest today in the lab is gallium oxide, and you see that is theoretical curve. So you see that gallium oxide material performance is just behind aluminum nitride and diamond. And another representation for power device, if we combine all important parameters for power device, for example, low on resistance, high breakdown voltage, electron saturation, and so on. I will not go in details, but the information from this figure is this pentagon, and the larger is pentagon, the better is the material for power devices. And if you see, the best is gallium oxide by its parameters, and you can notice there is no diamond, even theoretically is the best, but the reason is the cost as I mentioned, so if material is very expensive, any industry is losing their interest. And here is Yole's company, Yole's very nice representation, how different crystal diameter expansion versus years. And you can see, for example, diamond is still here, like below 1 inch wafer. And for example, gallium oxide is up to 8 inch already. Diamond is more than 20 years, huge effort, but still below 1 inch, where gallium oxide, 2012, people start working already. Here I mentioned 6, but in fact, there is 8 inch already in Japan. And here is a very nice representation from US Energy Department. They simulated and they showed if you compare silicon carbon-based device and the same device on the base of gallium oxide, you see there is a huge difference in cost, so $960 and $195. So why I show this, as I said, for future application, cost is really very important parameter, and the fact that gallium oxide is really very important material today in Japan and United States, and unfortunately much less in Europe. That is the reason that its performance and cost, this combination makes it very interesting, and especially for military application. So as oxide, gallium oxide, of course, is oxide and has the same problem as other oxides. To make it somehow p-type, it's very well doped, easily doped to be n-type, but challenge is p-type. But as I said, there is good surprise, and we had theoretical estimation, and we find out the enthalpy of formation of defects, donor defects, it's very low. If we compare, for example, with zinc oxide, which has permanent problem of p-typing. And this theoretical thermodynamic estimation was very good message for us to put effort in experiment, and in fact, it was done gross in Nanovation, which is small SME company in France, very close to Versailles. And after measuring in GEMaC, we find out that indeed gallium oxide was p-type, and we were, of course, very happy because it was first demonstration by us that it's possible to realize p-type conductivity in gallium oxide. So before this, all communities, they were very skeptic and saying that p-type conductivity in gallium oxide is not possible because it's very wide band gap, but fortunately it was done. And of course it was very interesting to reproduce this by another method, and it was done in GEMaC by Versailles and his colleagues, and we were very happy to find out that samples are very high quality and they exhibit also p-type conductivity. Even it was, we made annealing, post-annealing to increase conductivity, and it was really NDT is a very important step for realization of devices. And to make you idea where situates gallium oxide, what important is not only to be p-type, but also that mobility is very high. Very high when I say, I make reference to other oxides which have below 1 or 2 mobility, and gallium oxide has fabricated in GEMaC has around 10. And finally, question, of course, why we put so big effort? Where can be situated gallium oxide-based devices? I'm speaking about power devices at the moment. So here you see, usually we define by range, low voltage range, middle and high, by application. And in low voltage, we have more gallium nitride and high frequency application. And in the middle, silicon carbide and gallium nitride, they really compete. And so where is the place of gallium oxide? In fact, it's beyond silicon carbide. So gallium oxide pretends to exhibit very, very high breakdown voltage, more than 6.5 kilovolt, and theoretically it should be around 30 can be achieved. So today what we are working on in the lab to produce materials to put in evidence bipolarity, and we have a very nice collaboration to make power devices. Okay, at SCAPE we did some other work which forced to integrate gallium oxide in solar cell architecture. It was shown already, such a device. And finally, here to thank all my collaboration who are working on gallium oxide project. So thank you very much. And I find out that the Gallia, which is the name of gallium oxide, is not only gallium oxide, but apparently Parisian beer from 1890.
On va remercier encore, on va applaudir pour tous les intervenants.